Powell for their tireless organization of these sorts of meetings, and in particular to Ed, who, poor fellow, has not had much of an opportunity to enjoy the meeting itself due to his organizational efforts. So we have heard. Yes. How is Powell? So.
Sorry.
So we have heard about Emery's a number of times here, and so I'm going to begin by summarizing some of the processes previously discussed. And then, particularly because this is one of the last talks of the meeting, rather than giving answers, I'll pose questions. In particular, I'll talk a little bit about some issues that have been discussed a bit in some other contexts. Triaxiality, the possible net rotation of the core around the galaxy, how this could influence various rates. Talk about binaries and also star formation in disks, which might have a role to play in terms of EMRIs. Quasi oscillations, an effect known since 1960, but in this context relatively new, introduced in a recent paper by Antonini et al., including David Merritt. And then I'll talk about distinguishing between different scenarios, because as it turns out, it's very difficult to predict the rates and properties in advance. So if Lisa is going to do observations, what exactly is that going to do for us? So the story thus far, as we've heard from David, Tal, Miguel, and others scattered throughout this workshop, galaxies have supermassive black holes. At least there are some galaxies we know have supermassive black holes, and by generosity we'll extend that most galaxies have supermassive black holes. We talked about two-body relaxation, so simply objects that go past each other and deflect each other where there's a large contribution at big distances. This causes things like mass segregation, and if this were the only process that were involved in the production of extreme mass ratio inspirals, then it turns out you would end up with events which have fairly high eccentricities, specifically ones that are going to give you eccentricities of a few tenths within the Lisa band. So this would be clearly distinguishable and also quite complicated. Resonant relaxation, we've heard a great deal about that, including some of the recent interesting results. This plays a major role. This may be one of those bizarre circumstances in which when you conclude all the effects, it ends up not playing a particularly major role, but for now let's say it's playing a major role. And you have to have something else major to cancel it out. And although we haven't heard a lot about it, massive perturbers, for example, the progress of a giant molecular cloud or maybe an intermediate mass black hole or something like that through these systems can be important, particularly as it turns out for binary capture, and I'll revisit that a bit later. So what other effects might contribute? And so we'll start with some aspects of the core itself, and here is where we definitely have a variety of questions where we don't necessarily have the answers yet. So one question would be the role of net rotation. So here I have a graph which has been, some portions of it have been excised from Seth et al. And this is a relatively nearby galaxy, NGC 4244. We do have net rotation in the core. Now, why is this important? Let's revisit the issue of two-body relaxation. If you think about the effect of one object on another as they pass like ships in the night, they deflect each other, and if their relative speed is small, then they end up having a larger effect on each other. It's not so obvious maybe, but it turns out that the effective cross-section of interaction for a significant deflection is larger if you have a smaller relative speed. So two-body relaxation, mass segregation, these processes are enhanced if you have the relative speeds decreased. Now let's imagine that what you've got is a system where you're well inside the radius of influence. So that is to say you're in the region where the massive black hole's gravity is what's dominating everything. That means that the overall typical speed at a given radius is more or less the orbital speed. Now if you have complete isotropy of orbits, then you have a typical encounter speed like that velocity dispersion, the orbital speed. On the other hand, if you have a lot of net rotation, then the velocity dispersion is decreased. And as a result, you end up with smaller relative speeds. This is to say that if you have net rotation, then you can have faster dynamical effects, even of the classical sort. So if there's net rotation, the inner parsec, say, this region where you have the domination by the black hole, the relaxation times are decreased. Now there have been some simulations. As always, these are difficult simulations to do, so these are sort of the first wave of them, suggesting these could make a huge difference to rates and properties. And indeed, it is certainly true that if the rotation speed in the inner parsec or so is comparable to the expected orbital speed or velocity dispersion, you would indeed expect gigantic effects. But the question is, how common is this? And here's a situation where the observations are very challenging indeed. So if you're wanting to resolve the inner parsec, as a reminder, then at a 1 arcsecond resolution, your object has to be just 200 kiloparsecs away from you. So most galaxies are a lot farther away than that. So this means that observationally, we don't have much evidence. Our galactic center, this object, maybe a couple of others. So this throws it squarely into the ballpark of theoretical expectations, which, speaking as a theorist, is always a bit difficult and dangerous. And the question would be, if you end up with, for example, mergers of galaxies, would you end up with a net rotation which communicates itself down to the center? Bernard?
Is that gas or stars?
This is stars. So gas, of course, you see lots of evidence of rotation. The stars are what we're talking about here, at least for the moment. Another issue that we've heard a bit about in some previous talks is triaxiality. Now, it is one of the canonical aspects of astrophysics that all objects, when you first examine them, are spherically symmetric, just the way that in cosmology, all categories of sources are non-evolving standard candles. And it is only when you look more closely at them that they have deviations from these properties. So if we're again thinking about things like galaxy collisions, which is not a necessity for Emery's, it's something that you would think about for massive black hole mergers, for example. But if you do have big collisions, you can have triaxiality. So here's M87, a giant elliptical galaxy in the Virgo cluster, which you can eyeball and say is more or less triaxial. And the issue with this is that if you think it's first about a spherical system, the spherical symmetry that you therefore have means that individual orbits in a smooth spherical potential will conserve angular momentum in all directions. And if you have something that's not spherical but actually symmetric, then the angular momentum is conserved around that axis. And so it requires other things like interactions with a grainy distribution of stars in order to change the angular momentum of this. However, if you have a significantly triaxial system, then there are no such symmetries. And though, of course, the overall angular momentum of the entire system is conserved, individual orbits do not have to conserve this angular momentum. And indeed, you can get orbits that, from one orbit to the next, can change their direction of angular momentum. Or you can have the so-called centrophilic orbits, center-loving orbits that go straight through. Now, the issue is that although at large distances, like here, where you've got tens or hundreds of kiloparsecs, you can have very large triaxiality. Near the center, it's not as much so. For example, if you're deeply in the region, which is dominated by the potential of the massive black hole, the potential is very close to spherically symmetric as a result. So the question is, are you going to get increased feeding rates to the center, maybe boosting the Emery rate? And this is something that ends up being more important for binaries than for single stars. So as one of the items that Tal described is that if you think about the single star Emery, the one that is being moved around by two-body and resonant relaxation, then it turns out that the dominant contributor to that Emery rate is actually pretty close in, maybe 1/100th of the radius of influence, give or take. But as we'll describe in just a little bit, if you have binaries, then it's conceivable that you can have a significant contribution from farther out. So you might imagine that for binaries, the triaxiality issue could be more important than for single objects. So what about those binaries or other Emery sources? In some sense, you can define the three categories of Emeries that have been discussed. Emery Classic is single objects, like single stellar mass black holes, which undergo these various relaxation processes and eventually get close enough in their pericenters to the supermassive black hole that gravitational radiation starts whittling down the orbits and giving you tens of thousands or more of orbits within the LISA band. But there are other prospects as well. For example, suppose that it turns out that you have a number of stellar mass black holes that are in binary systems. Now, if that binary can manage to make its way eventually down close to the supermassive black hole, and can do so without ionizing, meaning being actually separated and made unbound by stellar interactions, or merging with itself, which would be a potentially interesting ground base like LIGO or Virgo source, then you can end up with in the binary being tidally separated such that one of the two objects comes into a closer orbit around the massive black hole and the other gets tossed to infinity. For those of you who have studied these things, this is a very promising mechanism for producing the so-called hypervelocity stars. This is something we suggested a few years ago. Another possibility, which is intriguing and indeed has motivated some of the studies that we've done with Nico about doing extreme mass ratio in spiral and very careful phasing, is the prospect that you can actually form stellar mass black holes in an accretion disk. So suppose that you end up with a massive black hole and around it is an accretion disk. And as we heard earlier, there are circumstances in which you could imagine that the outer portions of this disk would be unstable to star formation. And if this is true, and if in addition, as has been suggested, you might have a bias towards more massive objects being formed than usually, then you can form black holes. In the disk, the black holes are actually coupled hydrodynamically to the disk, and therefore as the disk spirals in, the black holes can be dragged with them. So this is another mechanism, and one big question there would be what fraction of the disk mass converts to stars. Is this a trivial, unimportant mechanism, or is it something that could actually bring in quite a large rate? So let's now talk about some of the aspects of binaries, and in particular, three-body interactions. So I'm going to define here hard binaries and soft binaries. So a hard binary is one such that an interaction of the binary with a typical other star in its vicinity has a net negative energy. That means that the binding energy of the binary is larger than the typical kinetic energy of whatever field star is coming by. That's a hard binary. For a soft binary, the net energy is positive, so it's the other way around. Now, people have done a lot of different simulations, starting in the mid-1970s, Douglas Heggie's thesis, for example. And the interactions that are close, that I'm cartooning here on the right, show that it is typical that a hard binary hardens. So in A here, I have my binary, I have my interloping object. We have some complicated interaction that could last for many orbits in that system, and eventually we resolve things. And what I've done here is that the final binary you see is actually closer together than the original. So this is the cartoonish version of a hardening of a hard binary. On the other hand, soft binaries tend to soften. You can actually show this analytically. So what this means is that the development of a binary can depend on whether it is hard or soft. Now, massive binaries, say a black hole binary, are in fact hard far out. If you're far enough out, parsecs away, then if they form and survive, they're hard. However, as they sink, because the orbital speed and therefore the velocity dispersion of the objects around them tends to increase, they're going faster, then if they maintain their properties, they would become soft from having been hard initially. Now, the characteristic hardening time, meaning, say, a time to decrease the semi-major axis by a factor of 2, is roughly the time to interact with the mass of the binary in the field stars. Now, this sinks also because it's heavy. If it's a black hole, it's heavier than the average star, and it sinks with some relaxation time. And something that my former student Vanessa Lawberg showed in her thesis is that the relaxation time is typically less than the hardening time by a factor of a couple. Now, what this means in practice is that you don't have much opportunity for hardening. You start out with your binary and it sinks, and maybe it hardens just a little bit before it becomes a soft binary. So therefore, it is not likely that you're going to be able to have binaries that, for example, are going to remain hard all the way down if they take a long time to sink, these potentials. So that is one of the reasons that I was saying earlier that if you have a process like involved with triaxiality of the system, that can take your binaries and send them down to the center quickly, rather than having to go through this long syncing process. It means that they are not going to have as much opportunity to soften and eventually to become dispersed. So that's one reason why the tidal separation process might benefit significantly. Another thing that is in the life and times of binaries is the Kozai resonance. Now this is a process which was originally proposed by Kozai for solar system processes. What Kozai noticed is that, at least in 1960, it appeared that there were very few short period comets that were highly inclined to the ecliptic of the solar system. And so it turns out that if you have, let's say, an inner binary, say the sun and comet, and an outer object in some stable triple, Jupiter in the case of the solar system, so you have something like here, we have our M0 and M1, or the inner binary, and then M2 is the outer object. Then in the proper inclination region, you can have a periodic effect that lasts for many, many orbits, and therefore is a secular effect. And essentially it means that the inclination of the binary goes up and down while it maintains its same semi-major axis. This is true for all secular effects. And it also maintains the same z angular momentum. The only way that this can happen if the inclination is going up and down is that when the inclination is relatively low, you have a high eccentricity to make the angular momentum low. So in principle, you can get to high eccentricity. However, general relativistic periocenter precession tends to limit this because it causes the phase relations to get dephased. So Doug Hamilton and I had a paper on that. So at best, you're going to have moderate eccentricities in, say, the LIGO band for realistic circumstances. For reference, this is a figure from a paper by Lin-Ching Wen in 2002, where we see that if we're looking in LIGO bands, at 200 hertz, you essentially have nothing but zero eccentricities. At 40 hertz, maybe a few hundredths. At 10 hertz, maybe a few tenths in a few cases. But what's the relevance for our particular situation here? There was a paper this year by Antonini et al., involving David as well, noting that in galactic centers, if you have a binary, and then that binary plus the supermassive black hole can actually act as a triple system of this sort. And to quote from their abstract, this can lead to large periodic oscillations in the internal binary eccentricity and inclination. Now this is interesting. It's something that may not be so much directly relevant for LISA per se, but if you end up with the system going to a very small pericenter state, then this might involve gravitational radiation. Perhaps you produce things like LIGO Virgo sources. So I've got a graduate student who's studying these and some other processes with Monte Carlo simulations, and David tells me that he and Antonini are also working on this. So hopefully this is something where we're going to get a better idea of how these processes all come together. But now we get to the question, how can we tell? So in one of the afternoon discussion periods of the Emery group, Tal gave us the rather downer but unfortunately realistic point of view that even if we somehow master all of the aspects of the dynamics of these systems, and as he actually said this morning as well, the input conditions are sufficiently unknown that it doesn't particularly seem all that likely that we are going to be able to have excellent predictions of rates and characteristics of all these Emerys. There's just too much unknown, and the observers are not going to be able to get their kilometer scale optical telescope to be able to resolve all these systems to tell us. So what about the inverse question, though? Suppose that in 20 years, those of us who can still walk here and see are looking at a long list of Emery events that have been detected with LISA. Can we do the inverse problem? What is this actually going to tell us? And for this, I think that there are a couple of things, and I'll go through sort of the three mechanisms we're talking about. One of these has to do with the expected eccentricities. As you know, gravitational radiation circularizes orbits. It turns out that when you're very close to the ISCO, that's no longer quite so much the case, but for very highly eccentric, you can do a simple impulse approximation to determine that you are going to circularize at a roughly constant pericentre distance. However, at the same time, you have interactions such as what we've discussed, two-body relaxation, resonant relaxation. These can increase or decrease the eccentricities depending on the precise circumstance. So how do these exactly play out? Well, here's my single equation to demonstrate that I can use LaTeX. And under pure gravitational wave evolution, the time scale necessary is dependent on the various quantities like so for reduced mass, total mass, frequency, and eccentricity. Now the point is that if you put in, say, the bottom range of the Lisa band and a stellar mass black hole into a 10 to the 6 solar mass object, E of 0.5 or whatever, the circularization time is maybe 1 million years. This is actually pretty short. It's shorter than at least the two-body relaxation time and can be competitive with the resonant relaxation time. So whether something circularizes or not depends, therefore, on the kind of input conditions. So I'm going to go through the 3 scenarios that I described for Emery's, and what I'll conclude ultimately is that these have different dynamical signatures. So depending on the eccentricity and the inclination relative to the spin of the black hole, you can actually distinguish these. And so the hope is that their different numbers and rates will in fact give you some semi-robust understanding of these galactic centers. This is Emery Classic. A high apocenter orbit is something where two-body relaxation or resonant relaxation causes is to go to a very small pericenter where it starts losing energy to gravitational radiation and eventually spirals in. For this to happen, the pericenter has to be small enough that it is often inside the Lisa band already. That's why you end up with relatively high eccentricities. Also, in terms of the inclination relative to, say, a spinning supermassive black hole, there's no reason for any particular preference. So, measurable, decently high eccentricity, arbitrary inclination. Triaxiality, as we said, is unlikely to boost this particular rate. The second point is the tidal separation that I was mentioning. So here we have a binary, and it goes past the black hole. Now the binary can be tidally separated and therefore leave an object near the supermassive black hole without any loss of energy at all. So it can happen at a much larger distance, and therefore it can have a significantly higher cross-section than the previous one I indicated. So depending on the fraction of binaries, this could be dominant over the single star, it could be very weak if it's a small fraction, and so on. But the nature of these orbits is that because these typically have large pericenters and fairly low apocenters, subsequent evolution is likely to circularize this before it ends up getting into the Lisa band. But the inclination of the orbits will still be arbitrary. So low eccentricity, arbitrary inclination would be a signature of this effect. And triaxiality might boost this. And then the third is the issue that I mentioned about settling in an accretion disk. Now I mentioned Uri Levin, where you can form stars and disks. There was an earlier suggestion by Morel-Descuda and Pallmeyer that you might have a pre-existing disk, stars in a nice wide range of inclinations, but as they punch through the disk, they eventually have to settle. And if black holes or neutron stars survive that, then you end up with something in the disk. Now you may know that the Bardeen-Pedersen effect tells you that for most of these systems, you're going to end up with the inner part of the disk aligned with the spin of the black hole. It's something that Priya and many others have worked on. In some cases, it could be retrograde. So you're likely to get zero inclination and, because it's coming in a nearly circular orbit disk, zero eccentricity. So this is something that has motivated some of the studies that Nico has led. So essentially, the thing I would say about the inverse problem is that you've got 3 different signatures. Essentially 0E, 0I, 0E, arbitrary I, significant E, arbitrary I. These sorts of things may help us be able to decouple these different processes. So in summary, there are several Emery scenarios that have been suggested. I say typically expect 1 to 100 at least the detections per year. Well, that is sort of throwing up of the hands, but it is true that people have tended to converge to that number, whether because it's true or because this is what would sell the mission. I'm not 100% confident. All of these do have major implications, as we heard, for general relativity tests and probes of nuclei, and there are a lot of open issues that have yet to be resolved. Thank you.
Questions?
I just have one question, Paul, on sort of the last scenario where you had the gas, the accretion disk, and you just briefly mentioned the idea of having it possibly fragment, having stars form inside the disk.
Yes.
Would you expect those stars, since they would probably be this top-heavy IMF, would they blow away the gas in the disk before they evolve?
This scenario has been examined, and the general feeling seems to be that you're going to evolve to a quasi-steady state. So not all the stars in that region are going to form at exactly the same time. And if you have, your one big guy which heats the disk enough, then it can become stable to fragmentation. So it's likely that you're going to get, to a situation where it's stable. Now that being said, there probably have to be some ways in which you can blow away the gas. If you believe that this is a mechanism by which you get the disk in the inner part of our galaxy.
Right. And then that might possibly change characteristics of whatever inspires that.
Yes, it's true. For example, being in the disk means that you have a common speed, and so you have a small relative speed like I was discussing earlier.
Other questions?
Well, I couldn't follow you on the Bardeen-Peterson effect. The Bardeen-Peterson effect is allowing the innermost region of the disk to align with the black hole spin
Yes,
out to a radius which can be significantly large, so
exactly.
300 m. But the disk is still very hot there, so what's the relation with the star you are thinking of?
So if the stars are dragged in with the disk, then by the time they get into the region where Lisa's frequency applies, the disk should already have aligned with the
Yes.
spin plane of the black hole.
Yes.
So the stars or the stellar mass black holes are going to come in orbits that are circular and inclined.